So please don't worry about the central part. This thing will be visible later. So I will start with using whiteboard for a while, just to demonstrate that mathematicians also can use whiteboards and not only computer presentations. So actually it was suggested to me by Elhanan that perhaps it's better if I show you some examples of other semigroups than only semigroup on the cube, just to give you some comparison, right? Because perhaps it will be more clear what happens on the cube if you see some classical semigroups related to physics, for example, or some other situations. Just we will more clearly see some analogies to what happens on the cube. So let's start with something very trivial. We start with our space being the real line with Lebesgue measure, the very trivial measure space. And now, once we have a function f, we make pt of f in the following way, that we just set pt of f at point x to be equal fx plus t. So we just use a uniform shift. We move in a uniform way in one direction, and we just move the graph of our function, more or less, right? This is the classical shift. So it's easy to check that this is actually a semigroup, in the sense that P0 is identity, and Pt plus S is equal Pt composed with Ps. In fact, this is a quite rare case of the semigroup that can be also defined for negative times and have good qualities when you move both directions. That's quite exceptional behavior with most semigroups. Inversion of time, you cannot really go. It's a group, right? So this is a very untypical property of this semigroup. Usually you cannot expect such things, but here we have even the same nice behavior for negative times. No problem here. And well, what is the generator now? Lf of x. So by definition, this is minus d over dt f of x at t equal to 0. So of course, when you differentiate it, you will see that this is just minus f prime of x. So in other words, we can say that the generator of this group is simply minus derivation operator. Of course, there is a question on which functions you can actually do the differentiation. And for example, we can restrict to continuously differentiable functions or smooth functions or whatever is your preferable space on which derivative would work nicely. So just to demonstrate what are the potential problems when you try to recover the semigroup from the operator, let me recall that on the cube there was no problem with writing this as an infinite series. Right? On the cube there was no problem. Everything was bounded and nicely convergent. So if we try to do that here, then we would get that PTF at point x should be, and when you implement this and you recall that the kth power of the differentiation is just taking the kth derivative, what we'll end up with will be just the following formula. Right? Which is not very surprising because this is just a Taylor's formula.
The first plus is a minus, right?
In fact, it will be plus because L is minus derivative, so these two minuses will cancel out. Okay? So we recovered the Taylor's formula. And what was my caveat? My caveat was that even if the function lies in the domain of the operator, it doesn't have to lie in the domain of operator squared and so on. But this example shows that even if your function lies in the domain of all powers of operator L, you still can get in trouble. Even if this formula makes sense, you still can get in trouble. Think about function f of x given by the formula exponent minus 1 over square of x for x different from 0 and 0 otherwise. Right? this is well known that this is a smooth function. You can differentiate it over the whole real line. It's C infinity function. And obviously this function has also the property that k derivative at 0 is equal to 0. This is quite easy exercise. That's first year of mathematics exercise usually, and you can do it on Scratch. So this shows, and actually when you try to apply the Taylor's formula, you easily see that you get in trouble, right? So this is an example of a smooth function that doesn't, well, it has a Taylor series, and it's a convergent, just because all coefficients are 0, but it's not equal to its Taylor series, right? In other words, it's not analytic, right? And of course, this is nothing very special to this function. Most smooth functions are not analytic. And this is how things are, simply. So this is an example warning that even for such a simple semigroup, recovering the semigroup from operator may be a difficult or at least tricky thing. So there is yet another thing about this semigroup that one should be warned about. So I told you before that one of the basic things that we would like to have is that when you apply the semigroup to the constant function equal to 1, you would like to recover 1. So of course this is satisfied by this semigroup. If you shift the constant function equal to 1, you get again this function. But if you remember correctly, I told you that usually we would like the functions on which we work to be integrable with respect to our measure. And in fact, we use it in our notation, right? So here, of course, the situation is completely different because this is not a probability space. Lebesgue measure is infinite, function 1 is not integrable, and so on. So in many practical situations, when people use semigroups in analytical context, there is a problem. For example, constant function may not lie in the appropriate class of functions. And, well, as you can see here, on real line, just with usual algebraic structure, the Haar measure is infinite, just because this is non-compact space. It's only locally compact, right? So this is just to show you that even in such simple examples, there are some things that somehow run out of the setting that we discussed. We discussed mostly things that happen on probability spaces, and in the case of the discrete cube, we really didn't have, fortunately, to deal with all those technicalities, but they will show up in almost every other setting. Okay, so if you want to get rid of the trouble of living in non-compact space, having unbounded measure, infinite measure, you can easily reduce this example and take everything modulo 1. Then you will live on a circle instead of the real line. You only restrict to one periodic functions, and you get the same semigroup, more or less the same operator. Right? Just derivative will be on circle with respect to rotations, right? And then everything becomes compact. Lebesgue measure restricted to the circle may be made probabilistic after proper normalization, and then things become better from some points of view, but still one can get in trouble when talking about the domain of the generator and recovering the semigroup from the generator, right? And this really is a bit more delicate issue. Okay, so now I would like to concentrate on two important examples coming from the world of physics. And actually, these examples are also important for historical reasons, because this is actually where the harmonic analysis came from. So all the Fourier series ideas, Fourier transform and so on, have their roots exactly in the two semigroups that I will discuss now. So first of all, there is something that is called Brownian motion. And I guess that most of you heard about Brownian motion. I will not give a strict definition of what it is. But I will just, for those of you who may not be very experienced with stochastic processes, I will just try to give a vague intuition what Brownian motion is like. So we start, we'll discuss things on the real line only. So we start at point 0, And we consider a discrete time. We'll take some very small times steps, and then we'll go with delta t to 0, and somehow Brownian motion will be what happens in the limit when delta t goes to 0, right? I will try to describe the finite approximation of Brownian motion. So what we do, we are at some point, and then with probability 1/2, we move to the right by a distance of square root of t, or we move to the left with probability 1/2 by a distance of square root of delta t. This square root normalization, this scaling is actually the appropriate one. Other powers wouldn't work that nicely. Okay? And then we just do the random walk. Right? We got to some point, and in the next stage, for the next delta t time, we move with probability 1/2 to the right by a distance of square root of delta t, and so on and so on. So this is a symmetric random walk on the real line. The spatial steps are square root of delta t. The temporal steps are delta t. And then we pass with delta t to 0. And what we get is some way of movement over the real line. Okay? And then you can prove theorem that such a limit exists, that the trajectories of a point with probability 1 will be continuous, that with probability 1 it will be nowhere differentiable, and so on and so on. Such object is called Brownian motion. This is not very trivial mathematical object. It took some time to mathematicians to establish the basic properties and to find a good definition. But anyway, once you get this sort of thing, you may look at this Brownian motion as a Markov process. And we discussed the connection between Markov processes and between semigroups, right? We know that every Markov process defines a semigroup, and conversely, every semigroup, under some technical assumptions, defines a Markov process. So we have this Brownian motion process, xt. I will call it actually bt. This is the standard way to denote it. Sometimes also wt, a Wiener process is used. Okay, so we have this Brownian motion, and then, of course, we recall that the way we recover the semigroup from the process is that we take expectation f, and now we should take this process starting from x and going for time t. Okay? But this is the same as just expectation of fx plus bt, right? Because if we start from a point different from 0, the whole image, the whole picture is just shifted by x, right? This is space homogeneous. Okay? And now, once you know this process, once you see that this is just a limit of such plus minus 1 symmetric random variables, it's very easy to prove that the distribution of bt at fixed time t is nothing else as the Gaussian random variable with variance t. Okay? So this expectation is nothing else than expectation x plus square root of t times g, where g is the standard Gaussian random variable n01. This is just the consequence of the construction of Brownian motion as such limit of Rademacher plus minus sums, and using central limit theorem. Nothing complicated here. Okay, so this is our semigroup. This is called heat semigroup. On real line. And now you can ask about the generator of this semigroup. So we need to compute the derivative. So I will assume that function f is nice enough, that it's smooth and it decays fast enough so that we can get with differentiation under the function f.
Would it make sense to turn this off and turn it on?
Yeah, I would like to do that, but I just don't know how to. And how much time it would take to recover. Excuse me. There's the question, can we switch the screen thing off for a while and then bring it back? It will not take much time. Thank you very much. Okay, so now we just differentiate the thing. So we get the derivative of square root t, which is 1 over 2 square root t, expectation f prime x plus square root t g. Okay, and of course g will come out when we do this derivation. Right, this is under assumption that everything can be done legally, right? So, there are some assumptions about function f must be done that this is smooth enough and the tail of derivative decays nicely, but this is a technical part. Okay, so now what we have here, we can just explicitly write down what this expectation means. We integrate over a real line f prime x plus square root t y exponent minus y squared y dy. We just use the knowledge about the density of the standard Gaussian random variable. But now we may notice that we have a term that is a derivative of a function in natural way. So this is just d over dy exponent minus y squared 2 with minus. Okay, y exponent minus y squared over 2 can be written as such derivative. So now we can integrate by parts. We can shift this derivative to the first term, and then the minus will cancel out. Again, under assumption that when we go to negative infinity and plus infinity, the term will disappear, right? We again assume something about function f, but it behaves nicely. And we end up at 1 over 2 square root of t, 1 over square root 2 pi, minus cancels out. When we differentiate this thing, the square root of t will come out, because we take derivative with respect to y. Here we have second derivative of x. And here that. So actually we end up, square root of t will cancel out, 1/2 remains, and what remains is the Gaussian density. So we have here just expectation second derivative x plus square root t g. But obviously, we are interested in the case when t goes to 0. We are just interested in the right-hand derivative at 0 to compute our generator. And when t goes to 0, this goes to 0. If you assume that function f has continuous second derivative, again under some assumption about tail decay, you see that this tends to 1/2 second derivative of f. Which means that the generator in this case can be reasonably thought of as minus 1/2 Laplacian. Okay, we discussed the thing on one-dimensional line, so this Laplacian is just the second derivative. In higher dimensional situation, you just consider Brownian motion in the n dimension, so that you run an independent Brownian motion in each coordinate separately, and then the generator obtained from such Markov process would be minus 1/2 of the Laplacian. So when you put things together, this means that the derivative over time PTF of x is equal to minus 1/2 PTF of x, and here we have Laplacian with respect to the spatial coordinate. Okay, so when t is equal to 0, this is exactly what we computed. But if t is not equal to 0, if we don't pass with t to 0, we end up here, and you just see that this thing is nothing else than the semigroup applied to the second derivative of f. Okay, this expression is nothing else. This thing is just the semigroup applied to the second derivative of f. Right? So you can read things this way. Okay. So if you consider the function gtx as ptf at point x, function of two coordinates, this means that d dt g is minus 1/2 Laplacian over xg. And this is the famous heat equation. That's exactly where the whole theory started at. So physicists were interested in understanding how temperature would disperse on the real line or on the plane, right? And the thing that, in fact, Fourier started with was the example of a metal rod, metal bar that was uniform. You have some initial distribution of temperature over it. And he was considering the case when both ends of the bar were put to a thermostat, say water with ice, and cooled to the temperature 0. And then the question was how quickly the temperature of the whole bar will decay to 0, right? Because that's obviously what physicists expected, right? That the whole bar will cool down to 0 if you keep the ends in the coolers, right? Water with ice. But the question was how actually that would look like. What time it would need, what would be the shape of temperature after some time, and so on. And quite quickly they got to the understanding that this is the equation that describes the thing. That if the second derivative with respect to spatial coordinates is negative, if temperature has a peak at some point, then in this place it should very quickly go down. And if it has a low place at some point, then it should quite quickly get warmed up by neighbors, right? And of course, that was some more systematic treatment about that. So, what are the morale of? So, I will not somehow refer to what Fourier was actually considering, because this case is a slightly different thing. You have some boundary conditions, and you end up with trigonometric functions. In our situation, it's slightly different. On real line, if you start with some distribution of temperature that is compactly supported, for example, if you have some smooth, or not necessarily smooth, measurable function, and it's compactly supported, you know what will happen on real line. The temperature will slowly go down and disappear in infinity. Right? That's quite natural thing to expect. This is completely different from things that happen, for example, on the discrete cube, that we'll think about in a moment, because the cube is compact and the temperature doesn't have any way to escape to. Right? On compact space, temperature cannot escape to infinity. On real line, the situation is different. So if you start with a compactly supported function, it will slowly, or fast, depending on the shape, decay and go to infinity. So, what is the morale? The morale is that you can quite reasonably think about the temperature of in such situation as a collection of many little particles. That was at the time of phlogiston theory yet, right? So imagine that at the place where the temperature is high, you have number of small particles of heat that is proportional to the temperature, right? And in the places where the temperature is low, assume that it's always non-negative, right? You can always do such shift of scale of temperature to make it non-negative. So you put small number of particles, large number of small particles, just so that the number reflects the temperature, the density of particles reflect the temperature, and then you allow each particle separately, independently from other, to move according to a Brownian motion. And then, what happens after some time? When you average, because of the law of large number, Pt of f, the image after time t, will be the averaged history of those particles, right? So actually, the fact that starting from Brownian motion and using this averaging over trajectories, that you come back to the heat equation, means more or less that you can treat the movement of heat as movement of independent particles, each of which is moving independently according to a Brownian motion, right? This is a quite interesting phenomenon that you can describe things this way. Of course, actually the heat in real physical world doesn't behave that nicely, right? In the sense that we know that this is not about phlogiston or some other separate physical quality, but it's rather about kinetic energy of thermal movements spreading from in the crystallic net, for example, right? But the description is very similar, right? And at some level of accuracy, this is a very good description of what happens when the temperature is moving. So, because this is called heat semigroup, and because this has this very nice physical interpretation, this semigroup that we defined on the cube is also called the heat semigroup. This is called the heat semigroup on the discrete cube, because it's as close as it gets. I told you that there is no Brownian motion on the discrete cube, just because the Brownian motion has trajectories that are continuous. On the discrete cube, by its very nature, it's not possible. But the Markov process that we described, the continuous time random walk on the cube that we constructed, is as close as it gets to the Brownian motion. It's time homogeneous and it's space homogeneous. It looks the same in all vertices of the cube. When you take the isometry of the cube, you use it to change coordinates, you will not see the difference in the behavior of the process, and it's time homogeneous. Right? The transition matrix doesn't depend on time. Okay? So this is as close as things can get to the Brownian motion on the discrete cube. Right? So this is called heat semigroup, and actually you can view it in a very similar way. Right? You have temperatures at 2 in power n vertices of the cube, and they undergo a similar thing, only you don't have nice Laplacian. Instead of a Laplacian of this form, differential which is not available, you need to use Laplacian of this form. Right? You look at the differences between temperature at point x and its neighbors, meaning the vertices in Hamming distance 1. This is as good as it gets. You cannot do better on the discrete cube. Okay? And now another important example that is also coming from physics to much extent. This is Ornstein-Uhlenbeck process. So now, again, I will first, I will again do this on real line, and I will again describe some intuition how this thing works. So you start from some point, not necessarily 0. Again, we have some time step delta t. And what we do, we are at point A, at time t. At time t, we are at point A. We move first to the point exponent minus delta t times A. So first thing that we do is we dilate everything, collapsing the whole real line towards 0. Okay? Of course, the scale of this collapse is very small. It's close to 1, because delta t, our step of time, is a small number. But we make this dilation collapsing things to the 0. And the farther we are from the origin, the larger the collapse will be, of course, because this is a linear dilation. And after that first step, you add the noisy thing, which is with probability 1/2. You go to the left by square root of delta t, and with probability 1/2 you go to the right by this step, square root of delta t. So actually here you can make the dilation by a parameter kappa times delta t, and if kappa is equal to 0, what we get is just the Brownian motion. Right? This is a limit case of the Ornstein-Uhlenbeck, when kappa goes to 0. And well, you can do this for different scalings. I will just take kappa equal to 1 just to avoid too many constants here. Okay? And then you repeat the procedure. So you dilate by a factor of exponent minus delta t, then you make a random move to the right or to the left, then you collapse again, make a random step, and so on and so on and so on. And then again you pass to the limit with delta t, you go with delta t to 0, and what you end up with is a new thing, which is a Gaussian process called Ornstein-Uhlenbeck process. So Now it behaves differently. Even though it's still on real line, just because of this collapse part in our move, things will not escape to infinity. And actually, whatever distribution you start with, whatever point you start with, it goes in distribution when t goes to infinity to the standard Gaussian random variable. Right? Whatever point you start from, after a long time, your position will be approximately normal. Okay? And of course, this means that the standard Gaussian measure is invariant under the semigroup. Okay, so now again, what is the semigroup? PTF at point x. Well, this is expectation of f of this process if we start from point little x. Now, I will not give the proof of that, but again, this is some use of the central limit theorem, more or less. The exact formula for that will be exponent minus t times x plus square root 1 minus exponent minus 2t g, where g is the standard Gaussian random variable. Okay, so you can see when t goes to infinity, this thing will stop to matter much, and we will end up just with expectation of f with respect to the Gaussian measure, right? So whatever temperature you start with, again, this may be viewed as a heat semigroup, sort of, but now the underlying measure with respect to which one should view the things is the Gaussian measure. So this is sort of, I want to pass this intuition to you, this is sort of compactifying the real line. Real line as a topological object, of course, is non-compact. But by putting on it a Gaussian measure, which decays very quickly, we sort of compactify it from the point of view of what happens under Ornstein-Uhlenbeck process. Okay? And
this also corresponds to some physical...
yeah, and in fact, the Ornstein-Uhlenbeck process may be also written down just as a time and space rescaling of the Brownian motion. I will not go into details, but well, this is the whole theory of the Gaussian processes. That definitely has also physical applications. And what is the generator in this case? So I will not make the computation, but generator at point x is x scalar product with the gradient of f at point x minus Laplacian of f at point x. This is so-called Ornstein-Uhlenbeck operator. So it can be computed directly. And again, you need function to be in some nice enough class to have this operator. The good thing is that many technicalities are easier in this case just because of this sort of compactification, and many things may be done more easily. And now, I just want to turn your attention to the fact that in many ways, what happens on the discrete cube is actually closer to the Ornstein-Uhlenbeck process than to the Brownian motion, right? So, in the first stage, I told you that our process, our time-continuous random walk on the cube is similar to Brownian motion as close as it gets. But actually, also, one can view this thing as very strongly related to the Ornstein-Uhlenbeck process. And what is the reason? Imagine that you have some function on real line. And you consider this real line with Gaussian density. So you can simulate this function in the following way on the discrete cube. You take the point x from negative 1, 1 to the power n, and you make a new function, g, on the cube. You make it from the function that ran from real line into real line, in the following way, that g of x is defined as f x1 plus xn divided by square root of n. So this is a symmetric function on the cube. It depends only on the sum of coordinates. So it's in a way a one-dimensional thing, but it lives on a discrete cube. Okay? And now you can apply the usual semigroup on the cube to this function. Okay? And then you can see what happens when n goes to infinity. And when you apply the cube, the semigroup, hit semigroup on the cube, to function g after moving things to the cube, and then you go back to the real line, just to read what happened to your function here on real line, if you use the central limit theorem, do some computation, you will end up exactly with Ornstein-Uhlenbeck process. Okay? So Ornstein-Uhlenbeck process is a limiting object of the random walk on the cube restricted to the symmetric functions, right? And it's quite clear that if you start with symmetric function whose value depends only on some of the coordinates, then after running this cubic hit semigroup for a time, you end up again with a symmetric function, right? So this is a good invariant family of functions. Okay? So in a way, this semigroup on the cube is much closer to what happens in the Ornstein-Uhlenbeck setting than with what happens in the Gaussian Brownian motion setting. Yes?
So, but there's no way to see a connection between the generators, right?
I guess if you have smooth enough, nice function, probably you can also recover things about generators, right? Because you have comparison between semigroups. But then you must put very strong conditions on F, probably.
But if you're restricting yourself to only symmetric functions, you're really not operating on the cube. Honestly, you're working with the integers 0 up to n.
Yeah, that's true. That's true. So actually you can also, under different scaling, and if you do the whole thing not on the cube with uniform measure, but you take the product of biased measure, which I didn't talk about and I will not have enough time to talk about, but you can leave the whole theory to work also for the biased cube. You take just negative 1, 1 with some 2-point measure, but not necessarily symmetric, and then you take the product. You can, after taking appropriate scaling, you can get as a limit the Poisson measure, right, on the integers, and then you can read the whole thing as the standard queuing, I don't remember the formal name. So the thing is, you have some number of customers, and then with some intensity in the time delta t, you will get a next customer. And those who are already present, each of them independently is served with some probability and disappear, right? So whatever number of customers you start with, after some quite quick process, you will get to the Poisson distribution. This is the Poissonian version of the Ornstein-Uhlenbeck. And in fact, Ornstein-Uhlenbeck can be also viewed after proper rescaling as a limiting object from this Poissonian thing that happens. Okay, so all of this is interconnected. Actually, you may first get the Poissonian thing and then pass from it to Ornstein-Uhlenbeck. Okay, so this is just to show you the connection between things. Of course, what happens on the cube is much richer than what you get on the Ornstein-Uhlenbeck situation. But this is sort of convincing you that there is no very good and universal analogy between what happens on the real line and on the cube. Because from some points of view, this semigroup behaves like a Brownian motion, but from some other point of view, it behaves like an Ornstein-Uhlenbeck. And neither of these parallels is perfect. I mean, both have some advantages and disadvantages, and actually this is a separate object that has its separate properties. And part of the problem is that you don't have a real gradient and you don't have a real chain rule when you work with functions on the cube. Only you have the discrete gradient, and things don't behave as nicely as on the real line for that reason. Okay, so that was the end of the physical and analytical digression, which was just supposed to give you some parallels and some understanding of what happens. Can you switch the screen? Okay, thank you. So now let's come back to the... So here are just, for record, facts from the previous lectures, just we'll need to use these formulas here and there. So now, what is the Poincare inequality? This is another concept that we'll be using now. So the classical Poincare inequality comes from differential equations, differential inequalities. So when you have some region in Rn, and what is important, the region is bounded, and you have some function whose support, compact support, is strictly included in D. So the function disappears before reaching the boundary of D. And you assume that this is, it has continuous derivative, continuous gradient. Then we can easily get this sort of inequality. You just use some integration by parts, some Cauchy-Schwarz formula, and you end up with this inequality. This is what was invented, at least to much extent, by Poincare. And in fact, similar inequalities were known earlier in mid-19th century. Physicists knew some variants of this inequality and used them in different situations.
This constant CD.
This constant depends on the size of the region, more or less, and shape of the region. It's not universal. It depends on the set D, but doesn't depend on a particular choice of function f, if only f is smooth enough.
So if you think of it also as a function of D, then it's kind of a Cauchy-Schwarz, where like the two terms on the right-hand side are the CD and the...
CD is just a numeric constant. Depending only on the area D on which functions live.
It's more like the spectral gap inequality.
Yeah, this is a spectral gap inequality of a sort. Right. The thing is that you don't assume that f has expectation has integral equal to 0. Instead, you assume that it disappears when it gets close to the boundary. But this is more or less equivalent. Up to change in constant, you can rescale things to move from one statement to another. Okay, so this is just to tell you where the thing comes from. It comes from this sort of consideration. But now we will consider something slightly different. So we assume that the function is integrable. We have some probability Borel measure on Rn, and we will say that it satisfies Poincare inequality with constant c if the variance of f with respect to the measure mu is bounded by this constant c times integrated square of gradient. This is called the Poincare inequality on Rn. And of course, again, you need some assumption about the smoothness of f just to give sense to the right-hand side. Okay? And we'll say that the measure mu satisfies the Poincare inequality if for all functions smooth enough, this inequality holds with this same constant c. Okay? If we have some uniform constant. So this is the inequality that tells you something about the measure space, about the properties of measure mu, rather than properties of individual function f. Which is sort of twist in the point of view, because the thing started rather from a tendency to say something about properties of a particular function, and now we want rather to say something about the measure space, using f as a sort of test function. Okay? So another difference is that here we have variance, so we sort of compensate for the expectation being non-zero. Right? We know that the variance of function is the same as the variance of the function shifted so that the expectation is 0. So this thing is shift invariant. If you shift f by constant, it doesn't change. So this is a slightly different setting than in the original Poincare inequality. Instead of thing disappearing close to the boundary, we get this sort of thing.
Excuse me, the top equation, you do or you don't assume that the expectation of f is 0 on D? I mean,
here we don't assume.
So in the top, because
in the original one you don't assume that expectation is close to 0. Instead, you assume that the function disappears when you get to the boundary of the set D.
Ah.
And then you do the integration by parts.
Okay, so that's the assumption.
These are two different ways of controlling the function, right? One, you can say that it disappears in the infinite or when you get close to the boundary of some set. And another way of normalizing the function is to say that expectation is equal to 0.
Okay.
And you can sort of replace one for another paying some price. But in our setting, we'll restrict to this. I just stated this for historical reasons and because in the community of differential equations, people would rather use this normalization in many situations, right? But actually, we'll rather keep to this statement. So we'll bound variance instead of the second moment, but in exchange, we don't have to care about the tail behavior of the function, right? Even if we are on an unbounded region Rn. Okay. So now, on the discrete cube, we can replace Rn by the discrete cube, and instead of the squared gradient integrated, we can take our discrete gradient. Let me just remind you that our energy functional looked like that. So if f is equal to g, the energy of a function f can be viewed as sum of the squared gradients, right? Here we sum up over all x and y's on the cube such that they are immediate neighbors. Right? The Hamming distance between x and y is equal to 1, which means we sum over all pairs of neighboring vertices. Okay, so this is sort of integrated gradient as much as it is possible on the discrete cube. Okay, so in our setting, we'll look for something like that. We'll prove that on our discrete cube, we'll prove the Poincare inequality with constant 1 here. Okay? And moreover, we'll prove that if the function on the cube is even, if it satisfies the equation f negative x equal to f of x, then we can get the Poincare inequality with constant 1/2. We can get a better constant 1/2 if the function is even. Okay, so now both inequalities are quite trivial. Let me show the proofs. So we expand our function f into the Walsh Fourier series. We recall that the second moment is just the sum of squares of all coefficients, and we recall that the expectation is the coefficient that is that has the index empty set. So therefore, we can write down variance as sum of all squares of coefficient except the one that comes with the empty set. And on the other hand, we have a very convenient formula for this energy functional over FLF, and we know that it appears in this form. We sum up the squares of the Fourier coefficients multiplied by S. Right? Just because our operator L acts as a multiplier and multiplies the Walsh Fourier coefficient standing at S by the cardinality of S, right? So we have explicit formula for the energy functional. We have seen the proof of that equality yesterday, 2 days ago. Okay? So now, just because cardinality of the empty set is 0, we can drop the term that is related to the empty set, and we end up here. So it's clear that this expression is not less than this expression, and we have proved the Poincare inequality with constant 1. Right? Just because these are non-negative terms, and this is always greater or equal than 1. So the Poincare inequality is a trivial thing. Okay? It's just a one-line proof. Now, to prove the second assertion, that when we have an even function, then we are able to prove the Poincare inequality with constant 1/2 instead of 1. First, let's note that when we have even function, then cardinality of all Fourier coefficients, then all Fourier coefficients related to the sets with odd cardinality will be equal to 0. We have seen this in Johann's talk several times, and I think it's quite obvious, just because this is even function, this is odd function, so the product is odd function, expectation therefore will be 0. Things will cancel out. Okay, so now let's see why our Poincare inequality with 1/2 holds true. By definition, by our formula for the energy functional. This is given by this formula. The empty set doesn't really count because anyway this factor disappears. So now that's the same as summing over all S with cardinality greater or equal than 2. Because for all S that have cardinality 1, the coefficients AS disappear. Right? Just because we assume that our function is even. So all Walsh Fourier coefficient standing at cardinality 1 will be equal to 0. So the terms disappear. So as well, we can sum over S with cardinality greater or equal than 2 instead of summing over different from the empty set. Okay? But now, for cardinality of S greater or equal than 2, this term is greater or equal than 1, and this is non-negative, so we end up here. Now, this again is summing over all S different from the empty set, for the same reason as before. And this is just the variance. Okay? So you see that the proof is almost as trivial as the previous one. Okay, so this is called the spectral gap inequality, or variance energy inequality. And the reason for that is that actually what we have used, we restrict our operator L to the subspace of functions that are functions with expectation 0, and we look for the smallest eigenvalue related to such a restricted operator, and this is exactly the constant that will appear in the Poincare inequality. Okay, this is a trivial spectral inequality for those of you who know a little bit about spectral calculus. And actually, this is quite important also in physics, this sort of inequalities, variance energy inequalities or spectral gap inequalities, because they are responsible for the speed of convergence to equilibrium. So for example, when you have this problem with temperature and you want to estimate how fast the temperature will go to 0 when it spreads on the real line, or when you do that on in some other situations, then this sort of inequality, Poincare inequality, will make it possible to prove the exponential convergence, and the speed of this convergence will be measured by the size of the spectral gap. This is a quite common physical situation. But I don't go into the details, just to show you where it comes from. Okay, so next thing that I will need at some point is an elementary inequality. I will not spend time writing into the blackboard, and I will not spend time proving it. The proof is contained in slides. This is elementary. I will skip it. But just for the record, there is such an inequality, and it's trivial. I mean, you sit down, you use the fact that it's homogeneous, differentiate several times, and you prove it. The proof is contained in the slides. And now, what we need this inequality for is something that is called Stroock-Varopoulos inequality. So, still we restrict to the discrete cube. And assume that you have a non-negative function on the discrete cube with uniform measure. L is our usual operator. Then the following inequality holds. And this I will write down for the record. It's the Stroock-Varopoulos inequality. This is very important inequality in the theory of semigroups. Actually, the same inequality holds true for any symmetric Markov semigroup, which is not as obvious as on the discrete cube. And the proof that I give you in the slides, and I will not follow this proof, I will skip that part of computation because it's technical. But actually, the proof can be used to deduce the thing on any symmetric Markov semigroup. So if you are interested into seeing how this thing works on the arbitrary symmetric Markov semigroup, you can read through the slides and you will see that this is nothing specific to the discrete cube. But how to prove this inequality on the discrete cube? Well, very easily. To write down this expression and this expression, you simply use this formula that allows you to expand the energy functional, the expectation of function L, another function, in the following form of such a sum. So you do that. So in these terms there will be f in power p over 2, and here you will get again f in power p over 2 over x's and y's that are neighbors. And on the right hand side you will get f in power p minus 1, f in power p minus 1, and here you will get f and f. And then you prove this inequality pointwise for any pair of x and y that are neighbors separately, and you just add up these things. So what inequality you will need for that? Exactly this inequality. When you write things down, the thing amounts to proving this inequality for each pair of x, y separately, and then you deduce the Stroock-Varopoulos. So I will skip the proof of Stroock-Varopoulos in general setting, but you can find it in the slides if you are interested. This is just what we will need. And this holds for any p greater than 1. And for f non-negative.
So for p equals 2, it's an identity.
Yes, for p equal to 2 it's identity, and somehow the case p equal to 2 is sort of special.
So is it tight, close to tight?
Yes, in a way it's tight. Although the way to see it is not trivial. So I told you that you can prove the Stroock-Varopoulos on any symmetric semigroup. So if you do that for an Ornstein-Uhlenbeck semigroup, and you recall that the generator is given by this formula, when you plug it in, you will see that actually you have equality in the Stroock-Varopoulos inequality. Whenever f is, say, positive and smooth enough.
For where is this equality?
For Ornstein...
For what time? What year? Which year?
That's a good question. I think it's from 80s, and Stroock and Varopoulos proved it independently, but in the distance less than a year, so it's considered their joint result in a way. And they use slightly different setting and so on, but that's basically, I think 80s. I don't remember. I cited in some papers, so I will check and tell you tomorrow, perhaps. That's not difficult to find out.
Just to understand, on the cube, the external cases, they are symmetric functions? Constant.
Well, if you want to get close to inequality on the cube, you want this inequality to get close to equality, just because you can emulate the Ornstein-Uhlenbeck thing on the cube by taking symmetric functions. You can get as close as you want to the equality case just by taking symmetric functions.
Okay, so the Ornstein-Uhlenbeck, what are the external cases there?
For the Stroock-Varopoulos? For the Stroock-Varopoulos, if you plug it in, you will see that you have equality for all.
Oh, it's an identity.
Yeah. Yeah, but there is some sort of cheating, because, well, you need function f to be positive, but on the other hand, you want gradient not to disappear, and for many functions changing sign, when you want to apply these things, there will be some cheating. So, but for a huge class of functions, there will be exactly equality. So if you are only interested in having Stroock-Varopoulos equality, you can get it for any p as close to equality as you want. But for some practical uses, you will get in trouble just because the gradient thing at some single point may go to infinity, or the Laplacian in some practical uses it's not as good as what I wrote here. But if you keep to strictly positive function and smooth enough, you will just get equality in the Stroock-Varopoulos. This is just one line of computation.
Something that is an identity on the rings?
Well, it's not that strange, because when you see how you use this elementary inequality, when the function is smooth enough, and you do this only over neighbors, you will see that this inequality that you use is close to equality. And when you add up, the errors will add up to something tending to 0. This is not as strange as it may seem in the first moment. Okay? So in a way, this is a tight inequality.
No, what I find strange is that somehow in the cube, what is equality or almost equality just drifts into one way and becomes a proper inequality.
Yes, and actually this is related to the fact that the gradient of the cube, the discrete gradient, behaves in a worse way. And in fact, this is sort of miracle that you can save the thing instead of equality, getting inequality, but in one direction. And actually, with Hanan, we had some papers, and other people had papers exploiting this inequality. So yeah, the proof is trivial, and you will find it in the slides, right? I don't want to get into technical detail, but this is like a few pages of computation.
So this inequality can't be reversed, right, with some other factor of p? Like, I mean, the left-hand side, the right-hand side can actually be arbitrarily large compared to the left-hand side.
Yes, for some functions, the right-hand side may be much worse than the left-hand side on the discrete cube. And I think even on Ornstein-Uhlenbeck, if you get function that takes value 0, it's not strictly positive, but it takes value 0, and the gradient behaves very strangely in the proximity of 0, you can also get something that is not equality any longer, right, in the limiting case. But if you are bounded away from 0 and function is smooth, then the Stroock-Varopoulos will just change into equality for the Oleszkiewicz. So this inequality in Stroock-Varopoulos is actually reflecting the difference between discrete gradient and usual gradient, and the fact that for the discrete gradient you don't have as nice chain formula when you take derivative of the product or composition of functions. You don't get as nice expression as for standard gradient, and that is what is hidden behind that. But this is very useful inequality just because it's so close to equality in so many cases. This is a very strong inequality. Okay, so now I would like just to describe two results from the probability theory. So one of them is Khinchin inequality that most of you probably heard about. So assume that you have some real numbers, a1, a2 up to an, and you add them up with random signs. So you look at the sums of the form plus minus a1 plus minus a2 plus minus an. And then, once you have such a random sum, when signs are chosen independently with probability 1/2, plus and minus, once you have such a sum, you want to compare its pth norm with a qth norm, when p is greater than q, greater than 0. And actually, famous theorem of Khinchin, which he proved when he was working on the law of iterated logarithm, but it was later used in many other situations, states that actually this is the case, that there is a constant depending only on p and q, but doesn't depend on the actual choice of coefficients a1 up to an, and doesn't depend on the number of coefficients, doesn't depend on n, such that this bound holds true. So this is quite unusual. Of course, always for p greater than q, you will have sp greater or equal than sq. But the Khinchin inequality tells you that you can reverse the order of inequality, just paying the price of some coefficient, but depending only on p and q. Okay? And actually, even something more is true. If you, instead of taking real numbers, take vectors from some Banach space or some linear normed space, and you do the same, again, the inequality holds true with some constant which depends only on p and q. This is the result of Jean-Pierre Cahan. Actually, this is an open problem. I promise to give some open problems. So this is probably a quite difficult open problem. It's not known whether these optimal constants that appear in Khinchin inequality and Khinchin-Cahan are equal. In all cases where both constants are known, they are equal. So
in all cases,
CPQ is equal to KPQ whenever CPQ are known if one of those is equal to 2. This was proved by Hageru. But in general, they are not known. So, for example, they are known if p and q are both even numbers, even integers. But even that is known only recently, I think. And this is known only in few cases. But whenever both constants are known, they actually are equal. And this is an old question. I think it was asked by Kvapin. It was never published, but it's a very natural question. Is the real case somehow extremal? And it seems like hopeless. So it's known that asymptotically these things behave in a very similar fashion. So when p goes to infinity, the ratio between these two things, no matter what q is, only below p, the ratio between these two things will go to 1. This can be controlled, but nothing more is known. Okay?
KPQ doesn't depend on the space F?
No, it doesn't. It works for all normed spaces uniformly. That's the point. This is the constant that doesn't depend on the space, doesn't depend on the choice of vectors and on number of vectors. It depends only on p and q.
The situation is when they line up, and the vectors line up.
Intuitively, that's the extreme case, but proving it. Well, there are some situations where you can prove that actually, for some particular Banach spaces, you can prove that the constant is the same in real case and in vector space. This is, for example, whenever you are in Euclidean space. This is a quite nice trick. You just use sort of embedding. You use Gaussian random variables to embed Gaussians into Euclidean space into real line, and you can prove that the Khinchin constant and Kahan constant in Euclidean space are the same. But if you want to take over all norm spaces, this is wide open.
So is there like a Gaussian?
There is a Gaussian equivalent of that. So you can replace Rademacher's plus minus 1s by Gaussians, and then it's known that these two constants are exactly equal. Of course, in real case, for Gaussians, you can compute, you have equality instead of inequality, and you compute, this is just the ratio between pth and qth norm of the standard Gaussian random variable. But actually, the same constant works in the vector case, and this is the consequence of the so-called S inequality, saying that among all convex sets of fixed Gaussian measure, convex symmetric, the slowest growth of the Gaussian measure will be for the symmetric strip, which translates more or less to saying that the real line is extremal. So the Gaussian, yeah, thank you very much. I should have thrown at you some big chocolate. The Gaussian case actually is known, and these constants are known to be equal in Gaussian case. So that's another reason to believe that in Rademacher case it should be similar, but somehow the methods from the Gaussian case completely doesn't seem to be transferable to the Rademacher.
So this fact that this pth and qth moment can be compared, even like it holds for symmetric plus minus 1, Gaussian, what other kind of...
Oh, for great many random variables. There is the whole theory of hypercontractivity of random variables. So both in real case and in this case, you can characterize the tail behavior of random variables so that this sort of inequality is satisfied. This is so-called hypercontractivity of the random variable, and there is a paper by Kvapin and Shulga, I think, which gives complete characterization in terms of tail. Of course, from tail behavior to getting exact constant is not possible, but to know that this happens with some universal constant depending only on P and Q, this is known and this is completely understood. But this is not trivial. And actually the conditions are quite awful, especially in the Banach space. But this is known. And well, you can in Banach space you can ask not only about real random variables, but for example for some linear transformations as coefficients. And then I think it's wide open, probably completely hopeless. But if you only ask about sums of real random variable times vector, then this is understood. Okay, so this is just the statement. There is a long line of people who proves the Khinchin inequalities with optimal constant, and actually Whittle gave one of the first proof, I think, in the 60s, and then without knowing his result, along 20 years, several people independently gave similar proof. So somehow it took some time to recognize Whittle's input in this theory. And actually for the Kahan inequality there are two key cases when the constants are known. So it's known that between second and first absolute moment the constant is square root of 2, and this is the same as in real case, and between fourth and second moment it's fourth root of 3. And I will show you the proof of both results for the Kahan inequality, for the stronger case. And you will see that it follows very easily from the properties of the generator on the discrete. Okay, so just to tell you that why these two constants are optimal. So even on real case, this constant is optimal just when you take two Rademachers with coefficients 1. Then it's very easy to see that you cannot beat the square root of 2. And for this constant, you just take equal coefficients and normalize, and by central limit theorem in some appropriate form, you see that you cannot beat the ratio between just what happens for Gaussian and this is the constant for Gaussian. Okay, so it's very easy to see that you cannot do better than this constant. But now the problem is how to prove the Kahan inequality with this constant. Okay, so now we take some vectors, some n vectors in some linear space, and consider some semi-norm. Or if you prefer it, maybe just a usual norm. Semi-norm is the same as norm, just you allow the norm of some vectors to be equal to 0. You want homogeneity, triangle inequality, but actually we can even weaken and not insist on the fact that the norm of vector equal to 0 implies that the vector is 0 itself. Okay? We can skip that condition. So when we have a semi-norm on Rn, we can restrict it to the discrete cube. Right? We can just treat the discrete cube, negative 1, 1 in power n, as a subset of Rn. Right? So we restrict this semi-norm to the discrete cube. And we produce this semi-norm just by taking the point x in Rn and multiplying xi by vi, well, these are our vectors, and then taking norm from our norm space. Okay? So I hope it's clear why I say that this is a semi-norm, not norm, because it may happen that these vectors are linearly dependent. And even if you start with a norm on your Banach space or your norm space, it may happen that, for example, v1 minus v2 is equal to 0. Right? And then for the vector 1, 1, you will have this semi-norm h equal to 0. Okay? So really this degeneration to the semi-norm may happen. Okay, so we define our semi-norm in this way for the point from Rn. We consider such a sum. And of course we restrict to the discrete cube because our coefficients are plus minus 1s standing by the vectors, right? So we only need this on discrete cube. And now it has trivial properties. First of all, this is non-negative pointwise. Before or after restriction doesn't matter, just because the norm is non-negative. And also it's even, just because norm is a symmetric function, is even function, right? So we have a non-negative even function on the discrete cube. Now, we'll prove less obvious property. We'll prove that we have a pointwise inequality that L of h is not greater than h. This inequality is not true for every function on the discrete cube. But we'll prove that this is true whenever this function comes from some norm. Whenever it's a restriction of a semi-norm on Rn. Okay, so I will actually give you two proofs of that fact. First proof is by triangle inequality. We just recall that we can write LF at point x as such sum over all neighbors y of x. So we do that for our semi-norm. So this is just a restriction of the semi-norm on Rn, so we can come back to this. And now we can bound like that, just because of the triangle inequality. Right? We have the sum of the semi-norm of vectors, and we know that this is greater or equal than the semi-norm of the sum of vectors. This is just a triangle inequality. It goes the inverse, the opposite direction, just because we have a minus here and here. Right? We sum over all y's which are neighbors of x, and we use the triangle inequality to estimate this sum from below, which gives us the estimate from above of this expression, because here we have minus. Okay? But now, when you sum over all neighbors of x in the discrete cube, all immediate neighbors of x, what you get is n minus 2 times x. Is it clear? Just check it on the vertex 1, 1, 1, 1, 1, 1, 1. Out of the neighbors, each neighbor differs on exactly one coordinate. So when you add up those neighbors, in n minus 1 summons, the coordinate will come with the same sign as in the original vertex, and in one case it will come with the opposite sign. So after cancellation you will get n minus 2 times x. Okay? So what we arrive at is that things will cancel out and we get just h of x, which is h of x. Okay? And we prove the inequality that we need. Just by the triangle inequality, nothing else. And this is just what I said about understanding this identity. Okay, and now another proof, which is not exactly the same as the previous one. We know that any semi-norm on Rn can be written as a supremum of linear functionals. This is just Hahn-Banach theorem. In fact, it's much easier because we are in finite dimensional space. It's quite elementary. Okay, so now for each of these functionals, when we restrict it to the Cn, we get just a linear combination of Rademacher functions, of degree 1 Walsh functions, right? What is a linear functional? It's a linear combination of the things that we have, right? So after restricting to the discrete cube, again it will be a linear combination, which is nothing else than the linear combination of coordinate functions, which is exactly the Rademacher sum. Okay? But we know that Rademacher's, namely Walsh functions that are indexed by sets of cardinality 1, by singletons, we know that for them the eigenvalue, when we use operator L, is equal to 1. Let me remind you that the eigenvalue of L is cardinality of S, and eigenvalue of the semigroup is exponent minus Ts. So when we apply our semigroup to function phi, that is linear functional on Rn restricted to the discrete cube, what we get is immediately exponent minus T of phi. This just acts as a multiplier with constant exponent minus T for any non-negative T. But now we know that our semi-norm is minorized by each of these functionals separately, pointwise. And our semigroup Pt is order preserving. So because of that, Pt of H, which is a restriction of that, is not less than Pt of phi, which is exponent minus T of phi. And therefore, we know that Pt of H is greater or equal than this. We have this for any functional phi from our family separate. So it's greater or equal than supremum over all family. But we know that supremum over whole family is just our semi-norm that we started, which after restriction to the cube we described by little h. Okay? So now let's compute the generator L of H. By definition, this is the minus right-hand side derivative at 0 of the semigroup. So this is the fraction that we need to take limit of. But now we know that this expression is not less than exponent minus th. So this fraction is bounded from above by this fraction. But this limit we can easily compute. This is just h. Okay? So we have seen two proofs, one using triangle inequality and the other using positivity preserving and a nice geometric structure of the semigroup over linear functionals. I think both approaches are sort of equivalent, but I think it's good to see how both of them work, because especially this second approach is useful in other situations, whenever geometric context comes into it. Okay, anyway. Now we will prove that the constant k to 1, the Kinch-Kahan constant between second and first moment, is square root of 2. And you will see that this is just few line proof. We know these three properties. H is our function that we want to estimate, our semi-norm generated by the function. Because the function is even, we know that the Poincare inequality holds with constant 1/2. Remember? We proved the Poincare inequality with constant 1/2 under additional assumption that function is even. But this is our case. Also, we know that LH is not greater than H, and H is non-negative. So pointwise, LH is bounded by H squared. These two inequalities show that H times LH is less equal than H squared. So we have also inequality between expectation. And that's the end. Here we have second moment, here we have first moment squared, and here we have second moment. After we put things back, we end up in the Kinch-Kahan inequality with square root of 2. Okay? So you see that this is a few line proof of the Kinch-Kahan inequality with constant square root of 2. And now, how to do the proof for exponents 4 and 2?
Can you see, by the way, where equality holds?
For this proof, yes, and I think recently the robustness was studied by some group of people. Also, some of them I think located at Berkeley.
I think in the
Yeah, but somehow I think it could be also read from the original proof. I think nobody cared actually, but I think now it was studied more carefully, and perhaps it was of some importance to understand what happens close to equality cases. Now, this inequality. Actually, the vector case here is much more difficult than real case. If you want to prove the constant C for the Khinchin inequality for real coefficient, this is just few lines of proof. You sit down, you compute everything, and you end up with some elementary inequality. There is nothing to prove. But in the vector case, it's non-trivial. Okay, so now we use the same trick that we used before, but for h squared instead of h. But h squared is again an even function. So again, we use the Poincare inequality with constant 1/2 to the function h squared instead of h. Now, we use the Stroock-Varopoulos inequality to bound this expression. So using this Stroock-Varopoulos inequality for p equal to 4, we can replace h squared LH squared by h in power 3 LH. Right? This is non-negative function, and for non-negative function we can use the Stroock-Varopoulos inequality. Why do we do that? Well, first because we can do that. Right? We cannot resist the temptation. Second reason is that, of course, we can bound nicely from above LH. Right? You remember that we have this pointwise inequality for LH, but we don't know the same thing for LH squared. So now we, again, bound from above LH pointwise by h, and h in power 3 is non-negative, so the order of inequality is preserved. So putting things together, putting this bound and this bound together, we end up by binding this difference, fourth moment minus second moment squared, by some constant times fourth moment. And after you cancel the constants, you end up. Right? So somehow you see that this Stroock-Varopoulos inequality must be very close to equality in real case, just because you know how this relates to the real Khinchin inequality. Right? And you see that in this Gaussian limit, things must be very delicate. So the way you use Stroock-Varopoulos is very close to equality in some cases, because you recover the optimal constant. Okay, so I still have 5 minutes, so maybe it's a good time to state the result, and I will start tomorrow by proving this result. So, what is the chaos? When you have some variables x1 up to xn, you can consider a polynomial in these variables with real coefficients, and you will say that this is of chaos type. I'm slightly abusing the usual definition. So what I'm talking about is usually called tetrahedral chaos. And chaos would be general polynomial, but for my reason, I will just, for my needs here, I will just call this chaos to make it shorter. So this will be a polynomial such that the terms don't appear if in power higher than 2. So, for example, x1, x2, x3 may appear in this polynomial with non-zero coefficient, but we don't want terms like x1, x2 squared. This is forbidden. Okay? We don't want powers higher than 1 to appear in. We only want such a polylinear terms to show up. Okay, and now, if we plug instead of these variables some independent real random variables, then we get some random variable z that is a polynomial in independent real random variables, and moreover, this polynomial is of chaos type. And such thing is called random chaos. And this is very important object. For example, when you study stochastic integration, multidimensional stochastic integration, knowing how to control such terms is of big importance in theory of probability. You need to know how to bound nicely this sort of expansions. But now, in our case, what will be important for us is that actually by nature the Walsh-Fourier expansion is an expansion of arbitrary function on the discrete cube into the chaos thing, right? Just because all Walsh functions are products of coordinates. So we are lucky because in the discrete cube every function is just a chaos, a random chaos with respect to the underlying uniform measure. Okay. This is not the case on any other actually product space. Only on 2-point spaces we have such a lucky situation. That's more or less the reason why people need to bother with Hermite polynomials and so on, right? Whenever you move to spaces higher than 2-point space, you don't have nice sequence of two polynomials spanning everything, identity and constant polynomial, right? This is the case for 2-point symmetric space, but nothing else. And then you need to have a larger sequence of polynomials, for example, Hermite polynomials for Gaussians, and then you need to tensorize them when you move to higher dimension. And things get complicated. But we are very lucky on the discrete cube. Everything is trivial.
So you're talking about multilinear polynomials, right?
Yes.
So I don't want to question the terminology, but like in computer science, like you just call it multilinear. So I don't see like the chaos aspect of it, or I mean, under chaos I mean
chaos is the name that comes just from the stochastic integration theory. In probability, this was considered because of the stochastic integration theory, and this chaos comes just from that theory, and that was used for as a name for expansions, especially the Gaussian chaos. The terms when you integrate with respect to Wiener process, especially against many Wiener processes, the terms that come out, Ito calculus and so on, this is called chaos. That has nothing to do with the chaos theory in terms of deterministic chaos, for example.
So
this is just a name.
That this polynomial map is somehow chaotic versus...
No, it has nothing to do with the dynamic property of the...
It's older, right? The name chaos is before the chaos that was popular in the 50s.
Yes.
And so on and so forth. So
Yes, I think that one
it's an older chaos.
is actually older.
That's how the Bible starts, no?
This is the older chaos from which the dynamical chaos emerged, and later sky and earth. Yeah. Yeah, but this is just to tell you the terminology, because in many probabilistic papers you may come up on this notion, and just to let you know what it means for probabilists. Okay, so now, tomorrow I would like to start from a very simple lemma. This is some elementary moment comparison. We'll prove that for any chaos we can bound the fourth moment by second moment squared times 9 in power d, where d is the degree of the polynomial. So whenever you have a Boolean you have a function on the discrete cube, real valued function, and you know that the Walsh Fourier coefficients disappear for all s with cardinality greater than d, then you know that this sort of estimate holds with constant 9 in power d. This appears in Ryan O'Donnell's notes under the name of Bonami lemma. And in fact, probably Aline Bonami was one of the first people to consider this sort of estimates. I don't know whether in exactly this form, but definitely the same sort of inequalities were considered by Aline Bonami. She was doing harmonic analysis, and perhaps even Rudin before realized this sort of estimates. Sorry?
Bonami was the first.
But this is usually associated with the name of Bonami, but because I tried to read through these papers, and it's quite difficult to see where the breakthrough happened. I guess probably Bonami was first to realize this phenomenon in this generality. Okay, so the constant 9 in power d here is not optimal. For example, when d is equal to 1, you can prove the inequality with constant 3, not 9. But this is the optimal asymptotics in the sense that when the d goes to infinity, you can prove that the dth root of this ratio in some particular case, for some particular function, can be bounded from below by 9. So even for small d, you can prove it with slightly better constant. Asymptotic growth like 9 to power d is optimal. And in the slides, I will not show you the proof, we will not have time for that, but in the slides there is a particular example of a function which is actually very simple. You just take all Walshes with degree d and you sum them and you can compute things directly and estimate. So there are simple examples showing that the speed of growth is actually optimal. Okay, so tomorrow we will start with the proof of this lemma, which will be just one screen, as you can see, and very simple. And then we'll pass to something more complicated that is called entropic inequalities and hypercontractivity. And well, I hope we will end up with proving hypercontractivity and seeing some applications to stability. I hope I will manage to do that. I will try to speak faster a little bit. Okay. So thank you.